Hello, and welcome to Inverse Trigonometric Functions Integration. My previous video was on the differentiation of inverse trigonometric functions, so we're going to see some of the same formulas. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an instructor at Doña Ana Community College. Chapter 5 comes to us from Larson's Calculus 11th edition. Section 5.7 is Inverse Trig Functions Integration. Now, we're going to let u be a differentiable function of x and let a be positive. So our a value is always going to be positive here. The integral of du over the square root of a squared minus u squared is arc sine of u over a plus c. The integral of du over a squared plus u squared is 1 over a times the arctangent of u over a plus our constant of integration. And the integral of du over u square root of u squared minus a squared is a 1 over a, the arcsecant of the absolute value of u over a plus c. And there are only 3 integral rules for inverse trig functions. And if you remember from the derivatives, the derivative of arc cosine of x is the exact opposite in sign. So it's a negative of the derivative of arc sine of x. So if those derivatives only differ by a negative, we only need these 3 because we can handle negatives without a problem, just factoring them out of the integral. And so we'll only have antiderivatives of arc sine, arctangent, and arcsecant. So let's find the integral. In order to find the antiderivatives, we have 3 forms. 2 of them have a radical in the denominator. So when I see a radical in the denominator, it must be an inverse sine or an inverse secant, because we're in this section and this section is going to be one of those. Due to the order of subtraction, a constant minus the variable, it must be the inverse sine. So we're going to fit our form with a's and u's and make it all work out for us. We'll let a squared be 1, so that a equals 1, a is always positive. U squared equals 4x squared, so that u is 2x. What do I have to square to get 4x squared? I have to square 2x. Now the derivative of u is 2x dx, but I don't have an extra 2 hanging out here. So I will divide by 2 on both sides. 1/2 du is replacing dx. So my integral of dx over the square root of 1 minus 4x squared is, dx is replaced by 1/2 du. The square root of 1 minus u squared, and I could call that a if I wanted to, but our a is 1. I very rarely actually change that to an a. The 1/2 stays. I know this form is arc sine, and it's u over a, so 1/2 arc sine of u over 1. Let's reverse our substitution. We know that u is 2x. So 1/2 arc sine of 2x plus c. Notice the denominator of 1 no longer needs to be written. Don't forget your constant of integration. For the integral of 12 over 1 plus 9x squared dx, when I know I'm looking at inverse trig function integrals and I see there's no radical, it has to be inverse tangent. Once I know which one, I try to fit the form. Let a squared be 1, so that a equals 1. U squared is 9x squared, so what do I square in order to get 9x squared? That must be 3x. The derivative of u is then 3dx, or 1/3 du is dx, since I don't have an extra 1/3 hanging out here. So the integral of 12 over 1 plus 9x squared dx, I could take the 12 out in front. The integral of 1 over 1 plus 9x squared, I replace dx, don't forget the dx. I replace the dx with the 1/3 du. Still have my 12 out there, so 12 over 3 du. And my integrand, 1 plus u squared in the denominator. 12 over 3 gives us the 4. The form, the integral, using arctangent, will be 1 over a, so 1 over 1, arctangent of u over a, plus our constant. 4 times 1 is 4. Replace u with our 3x, and I have 4 arctangent of 3x. Remember, you could always take the derivative of our integral and make sure it matches up to the original integrand. And don't forget your constant of integration. The integral of 1 over 4 plus x minus 3 all squared. You were expecting a secant, weren't you? But it's not. Since there's no radical, it must be an inverse tangent example. In this case, a squared is 4, so that a is 2. We'll let u squared be x minus 3 all squared, so that u is x minus 3. Then the derivative of u is just dx. Now when I make my replacements, the integral of 1 over 4 plus x minus 3 all squared dx is the integral of 1 over 4 plus u squared du. Because of this form, right, I know it's arctangent, so it's 1 over a is 2, 1 over a arctangent of u over a plus our constant. Replace u with x minus 3, and we have our solution. 1/2 arctangent of the quantity x minus 3 over 2 plus c. Finally, we have an integral that will give us an arcsecant. So the integral of 1 over x times the square root of x to the fourth minus 4, all that in the denominator, dx. I see a variable outside the radical, so I'm thinking it's probably inverse secant. But when I see inside the radical, variable minus constant, then I know that it's an arcsecant form, so we have to match it. A squared is 4, so that a is 2. U squared is x to the fourth, so that u is x squared. Taking the derivative of this equation, we'll have du equals 2x dx. And even though we do have this x hanging out, notice that's in the denominator, so it's not being multiplied by x. So what I'm going to do is I'm going to divide both sides by 2x. So I'll have 1 over 2x du equals dx. Now, our original integral, right, and I did the math professor, I forgot to put in a du or a dx or a d anything. Bad notation. If I replace a dx with 1 over 2x du, I have my x to the fourth replaced by u squared. I can deal with these x's. That 1/2 comes out in front, no big deal. 1 over, now x times x in the denominator gives me an x squared. Square root of u squared minus 4 du, but notice here du. I want everything in terms of u. Hey, look at that. My x squared is u. So I can rewrite this. So my integral is all in terms of u. I've now matched the form completely. The 1/2 stays out in front. The antiderivative of this form is 1 over a, so 1 over 2, arcsecant, absolute value of u over 2, plus a constant of integration. That's 1/4 arcsecant, absolute value of x squared over 2, and plus c. Don't forget plus c. Of course, the absolute values are not necessary around the x squared, since x squared will be non-negative anyway, but I put it there just for consistency. The integral of sine of x over 7 plus cosine squared of x dx. Part of me says, hey, let u be this denominator. Maybe it's a natural log type of integral. And it's not. I'm in the section for inverse trig functions, so there's no radical. I'm just going to assume it's a tangent function, inverse tangent function. So I'm going to let a squared be the constant 7, then a is the square root of 7. I'll let u be the cosine of x, then du is minus sine x dx. Alright, sine of x dx, I can replace this. That's going to be a negative du. I have to take care of my negative. 7 plus u squared. I know that this, I could write it in a positive version, probably is arc cotangent, but we don't do that. I have the negative 1 over a, so 1 over square root of 7, arctangent of u over a, plus my constant of integration. And that can simplify as negative 1 over square root of 7 arctangent cosine of x divided by square root of 7 plus c. And of course, if you are used to rationalizing denominators, you should do so. But that's algebra, and I'm talking about the calculus of it. So if you get to here, I'm pretty happy. Alright, so let's make this a little harder. We want to find the integral. And the integral we're looking for, the integrand, is 4x plus 3 over the square root of 1 minus x squared dx. This in no way resembles any of our forms. I'm thinking that the 1 minus x squared, that looks like it should be an arc sine, but arc sine doesn't have a variable in the numerator. So what we'll do, ignore this for right now, that's going to be our bottom row answer. What we're going to do is remember that for a single denominator, we could split up a numerator. So instead of 4x plus 3, as my numerator, I could look at the integral of 4x over the square root dx plus the integral of 3 over the square root dx. And I'll take care of them one at a time. In blue, I'll let u equal 1 minus x squared. Then du is a minus 2x dx, and I can handle that x. The 4x, the integral of 4x over the square root of 1 minus x squared dx, the 4 comes out in front. My x is replaced by a negative 1/2 du. I didn't do that switcheroo right here, but that's what's going on. This is u to the 1/2 in the denominator, which is negative 1/2 of 4 is negative 2. U to the negative 1/2 du. And I know that the integral of u to the negative 1/2 is u to the positive 1/2 divided by 1/2. Yep, I missed a sign right there. This sign should be negative, shouldn't it? My negative from here, when I add 1 to my exponent in integration, I'll get u to the positive 1/2. And I'll divide that by a positive 1/2, which is the same as multiplying by 2. So I forgot a negative here and a negative here. And I'll be honest, I didn't forget it. I just missed it. Totally missed it. So minus 4, u, replace u, and we have square root of 1 minus x squared. Our form for the second part, the integral of 3 over the square root of 1 minus x squared, bring that 3 out in front, and this is the definition of the arc sine, all right, with an a value of 1. So my original integral, I found it in pieces. I found the solution as negative 4 square root of 1 minus x squared plus 3 arc sine of x plus c. So split it apart. You could always split a numerator apart by keeping your denominator together. Remember, you can never split apart a subtraction or addition inside of a radical, so that's not a valid switch. Find the integral of x minus 2 over x plus 1 all squared plus 4 dx. So we just saw an example where we split the numerator, but this one is not helpful, and if you'd like to, you could pause here, check it out, see for yourself. I'll wait. Just kidding, that's pause, I don't have to wait. What we're going to do is use a double substitution. I just didn't want to waste your time with splitting the numerator and showing it doesn't work. We'll let u be x plus 1. Then du, if we had a space in there, would equal dx. But more importantly, x can be solved for, and x is u minus 1. So, taking our original integral, I'll replace x with u minus 1. I'll replace x plus 1 with u. Simplify my numerator. I'll end up with the integral of u minus 3 over u squared plus 4. And now I'll split the integral u over u squared plus 4 du minus the integral of 3 over u squared plus 4 du. So I couldn't do it here, and you should satisfy your curiosity as to why it would not work. Then we do a double substitution, and now we can split it and see what happens. So from the last page, if we take a look at this first integral of u over u squared plus 4 du, I'll let w be u squared plus 4. Then dw is 2u du and 1/2 dw, right? I don't have an extra 2 hanging out here. 1/2 dw is u du. All right. So the integral of u over u squared plus 4 du. I replace du with 1/2 dw. Takes care of my u du, 1/2 dw. U squared plus 4, that's my w, so that's 1 over w. And look, we do have an integral that gives us 1/2 natural log of absolute value of w plus c. Remember, w is u squared plus 4. And remember what u is, because we'll have to use that as well. Now, all right, so we figured out we could unravel our substitutions, and we can get there. Minus. the integral of 3 over u squared plus 4 du looks like an inverse tangent form, where we just take the 3 out in front. Remember, since we're adding, it doesn't matter if it's a squared plus u squared or u squared plus a squared. So the antiderivative of 1 over u squared plus 4 du is, we still have our 3. Our a value is 2, so we'll have 3 over 2, arctangent of u over a, so u over 2 plus c. Together, this gives, should have been in black, but I forgot to go back for that. Our original integral is 1/2 natural log of, and in place of w, I'm going to use u squared plus 4, but remember u was equal to x plus 1, so that's 1/2 natural log absolute values, x plus 1 all squared plus 4, minus 3/2 arctangent of, and u was x plus 1, over 2, and a single constant of integration. Two constants add together to give me just a generic constant. That was a good one, right? Double substitution, and then look at individuals. Now some definite integrals. The integral from 0 to 1 of dx over the square root of 4 minus x squared. I know that this is the arc sine form, a value of 2. So this is the arc sine of x over 2 evaluated from 0 to 1. Substitute your 1. Substitute your 0. The arc sine of 1/2 is pi over 6. The arc sine of 0 is 0. Pi over 6 minus 0 is pi over 6. When it comes to evaluating these, remember, if you need to go back to pre-calculus and remind yourself of how to do it, do so. That's on you. If I want to evaluate the integral from square root of 3 to 3 of 6 over 9 plus x squared dx, I factor out my 6. My a value is 3, otherwise it's the inverse tangent form, so I'll have 1/3, 6 times 1/3 arctangent of x over 3, evaluated from the square root of 3 to 3. Pretty ugly looking 3's, but you know, we're there. 6 times 1/3 is 2. Arctangent of 3 over 3 minus 2 arctangent square root of 3 over 3. Arctangent of 1 is pi over 4. Whereas arctangent of the square root of 3 over 3 is pi over 6. So 2 times pi over 4, that's pi over 2. Minus 2 times pi over 6, that's pi over 3. Pi over 2 minus pi over 3 is pi over 6 when we get common denominators. Inverse tangent. If you need to review it, review it. And our last example. The integral from 1 to 4 of 1 over x square root of 16x squared minus 5. Alright, because of the variable outside, because of the order of subtraction inside the radical, I know this is the arcsecant form. So I'm going to let a squared be my 5, then a is square root of 5, a is always positive. Let u squared be 16x squared, so that u equals 4x. X equals u over 4, I'm going to also make a substitution here. And the derivative of u is 4 dx. Now, anytime we substitute, we're going to substitute twice. And the second substitution for definite integrals happens at the beginning. When x is 1, u is 4. When my x value is 4, u is 16. So when I take my integral in x and I rewrite it in terms of u, my limits of integration must also be in terms of u. U is 4x, du is 4 dx, but I don't have an extra 4 hanging out here. So that's 1/4 du, 1/4 du that replaces dx. My limits of integration have changed from to be 4 to 16. 1 over, and then I put u over 4 in place of my x. Alright. Square root of u squared minus 5. And we've already discussed the du. Simplify that a little bit. U over 4, a fraction in the denominator, multiply by the reciprocal, I'll have 4 over u, this 4, and this 1/4, cancel each other out. This form is arcsecant of the absolute value of u over square root of 5, my a, 1 over a, arcsecant of absolute value of u over a value being square root of 5. Substitute 16, and then substitute 4, And yep, I'm going to leave it exactly like that. If you're the type that likes to rationalize your denominators, you should do so. I not only ran out of space on here in order to make it legible, I also ran out of desire. I'm not a big fan of rationalizing denominators. Historically, we do it because we didn't have calculators for most of math's life. And now that we have them, I personally believe that rationalizing the denominator is a little bit of an archaic tradition. But a lot of people still require it. So make sure you know what your professor wants and expects from you. You should always do what they do and not just assume my laziness is common amongst everyone. That's it for inverse trig functions with integration. Thank you for listening.